자꾸. 했던 거네. 했던 건데 또 어려울 것 같아. You intercepted a secret message encoded as a string of numbers. The message is decoded via the following method, like this. However, while decoding the message, you realize there are many different ways you can decode the message, because some codes are contained in other codes, like this. 그리고 베이스 케이스는 DP 0은 DP 1. Okay. Shut up. 허허. One, two. Number of ways you can decode it. So this one, 226 or 226, right? Or 226. 226. 여기서 이게 DP 잠깐만. 자, DP1이 2나 22다. 그러면 DP DP2는 2나 22나 226나 226나 226네. 그래서 DP1 플러스 DP1 플러스 DP0이잖아. DP1 플러스 DP0. 왜 2가 나온 거지? DP1 플러스 DP0. 응? 왜? 10보다 큰데? 뭐야? 10보다 크잖아. 22인데 10보다 크잖아. 이제 1이구나. 아, 잠깐만. 뭐야? 그러면 (0이라고) 06. 아. 만날 수 없어. 만나고 싶은데 그런 슬픈 기분인걸. 만날 수 없어. 만나고 싶은데 하는걸. 나나나나나나나나나나나나. 아, 공이 없는 거잖아, 그지? 아하, 이거 그냥 공이 if S0 is greater than or equal to. 잠깐만. 케이스가 있네. 세 케이스가 있어. 0이 안 되는구나. 0이 없구나. 그러면 3 cases. 1. dpi si equals 0. Then it has to be then si plus si minus 1 must be in between 10 and must be greater than in between 10 and 26. Number 2, else 0. Number 2, si is greater than or equal to 1. Then 호호. 어쩌노? Wait, how is it? Yeah, that's 1. What? 엘리프가 아니야. if. What? catch me, catch me, catch you, catch you. 알아. 어? 1 1 1 2 1 2 2 dpi-2 01 아하 아 왜 이게 공이 왜 나오는 거야 도대체? 공이 왜 있는 거야? 공 이게 왜 1인지 이해가 안 돼. 어디서 1이 되는 거야 이게? This is 1? How? 아. First of all, I just need, yeah. Yeah. 여기에 일단 이거 넣고 그 다음에 아1 DP1은 일단 2야. 아, 잠깐만. 진짜. 1. 1에 this zero. 왜 이런 거야? 어? 뭐야? 왜 이런 거야? 그래. DP 01. 아. DP2부터 해. DP2부터 하고. 아, 잠깐. int. God damn, int. Two, right? Two. 이거 하지 마. 그냥 얘로 해 그냥. 이걸로 하고 1을 굳이 그럴 필요가 없어. 내가 봤을 때 0만 해 0만. P0을 1 if int s 0 is greater than equal to 1 else 0. 토락? 왜? What's going on? Okay, whatever. Keep going. Keep it going. Keep it going. Here's some word break. 아니 아이로 하자. 아이. 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 이게 렌티. 오호, 나이스. 나이스. 300. Longest increasing subsequence. 야, 내가 이거 6을 언제까지 할 수 있으려나? 6을 4시까지 할 수 있으려나? 6을 5시. 9시하고 5시. 8은 내일 해야겠네. 8 내일 하는 걸로 쇼고 가. 8 작잖아. 으이그 300. 일찍 일어나지 그랬어. 당근을 왜? 스택으로 하는 거 아니니 이거 그냥? 아, 안 되겠네. 아, 스택은 안 되지. 아니지. 왜 안 돼? 서브시퀀스가 뭔데? (01) 0123이야? 아, 그래. 올라서서 파란 하늘 바라보며 합니다. 어? 얘 2. 이 왜 2야? 아, 산까지 올라 뭐야? 아 진짜. 아 브레이크를 못하네. 아 짜증나. 아니 브레이크를 못해. 세상 이게 맞아? 몇 개야 몇 개? 될 것 같네. 어? 2, 3, 4, 5, 6. 아. 어휴. Can't I collapse it? 아 뭔가 더 빨리 할 수 있을 것 같은데. keep 힙을 하자고. 그래. 아 그럼 안 되지. 이게 더 작을 수도 있잖아. 계속 푸시해야 되는데. 아니야 좋지 않아. 좋지 않아. 좋은 결정은 아닌 것 같아. 그냥 여기서 만족해. 아 내가 이게 DP라고 안 했으면 DP인 줄 알았을까. 모노토닉 스택으로 어떻게 나가려고 했을 것 같은데. 할 수 있는 01, 03, 23, 이게 리니어잖아. 아, 리니어는 아니네. 리니어는 아니긴 해. 이렇게 되면은 루프가 세상에. 루프가 어떻게 되지? 오연이? 바이너리 서치. 바이너리 서치를 하길 바래. 상상도 못했다 진짜. 어떻게 바이너리 설치냐 이게? 어. 바이너리 설치가 아니라 그냥 바이섹트는 끝잖아. 바이섹트에서 그냥 끝잖아. 지켜. 그래도 우리가 1을 넣으려고 해. 그러면 아니면 03 이렇게? 02, 01, 3 아니면 01, 2 01, 2, 3 choose this one or that one. 그 choose를 하려면 다이나믹 DP가 무조건이다. choose는 무조건 DP다. 약간 그렇게 생각을 해야 될 것 같아. 무조건 모노토닉 스택으로 하려고 했을 것 같아. 웬일이야 이게?
우리 오늘 그거 선물 받았어. 과자
아하,
선물
그렇구나.
세트. 그래서 엄마가 오레오랑 그거는 가져왔지 체린 주려고.
그렇군. 자, 이제 네트워크 섹션 6를 해볼까. 아, 네트워크 진짜 싫어하기. 아, 네트워크 정말 싫어. 네트워크 generalized forwarding and internet routing. 오, my god. 7까지만 하자. 와, 7도 왜 이렇게 길어? 미쳤어 정말. Network layer, IPv4, IPv6, and router operation. Take a break. Let's take a break. 아, 백그라운드 뮤직을 좀 틀어야겠군.
Let me tell you something. This isn't a
엄마 내 방송 들어가 봐.
지금?
음악 나오나? 들어가 봐.
어디로 들어가? 스키방에서?
아니 내 거 없어? 지금 있어야지 지금 정도는.
없어. 나는 안 떠. 호텔 스터디 위드냐? 이름이?
잠깐만 여기야 여기.
업로드가 삭제한 동영상.
여기로 들어가.
유튜브에서?
아니 내가 그 장씨 가족에 올렸어.
호텔.
아니 장씨 가족 방에 들어가 봐. 장씨 가족. 거기 들어가 봐.
이걸 어떻게 해야 돼? 구독 이런 거 나는 안 된다? 구독이 안 돼. 구독 좀 시켜줘봐. 응? 왜 돼? 또? 좋아요가 안 되던가? 희한하네.
안 들리네?
엄마?
아니 잠깐만.
Let me tell you something. This isn't elementary school. This is hard work. Long hours. High pressure. I need a grown goddamn man.
You give me this, and I will work as hard as it takes to school those Harvard douches and become the best lawyer you have ever seen.
I'm inclined to give you a shot, but what if I decide to go another way?
I'd say that's fair. And sometimes I like to hang out with people who aren't that bright. Yeah, just to see how the other half lives.
Move over.
뭐가 들려야 돼?
I'm emailing the firm I just found our next associate.
왜 들려야 돼?
백그라운드
이게? 이게 말하는 게?
말은 이제 없어질 거야. 기다려봐.
한 명도 안 들어왔니?
다 나갔어.
좋아요 두 명밖에 없네.
백그라운드 뮤직이야. 좋아요를 누가 했어?
나 말고 누가 한 명이 해.
들어가긴 들어왔나 보네.
시청자 수는 하나밖에 없어.
들어왔다 나갔다 하는데 저번에 엄청 많이 들어왔었는데 안 들어와 이제.
재미없나 보네.
재미없지 뭘 재밌어. Forwarding, routing, and control.
구독자는 14명이네.
구독자는 좀 늘었어. Forwarding, routing, and control. Forwarding. Where should this packet go now? Local table and lookup and action in the table. Routing. What paths or reachability should the network use? Distributed protocols or controller applications just state. Destination base route. Which outcome matches this destination prefix? 그냥 끌까? 백그라운드 음악?
너무 너무 커. 백그라운드 음악이 너무 커가지고 뭐 들려 이게?
그러면
네 목소리는 안 들리고 백그라운드 음악만 크게 들려.
그 정도로. 오케이. 나 이제 GPT랑 대화하면서 할 거야.
엄마 나갈게.
Okay, now the next section is on generalized forwarding and internet routing.
Okay, let's step through it. Generalized forwarding is the idea that a router isn't just doing classic IP destination-based routing. Instead, it matches on multiple header fields: source, destination, protocol, ports, maybe even application level info, and then takes some action like forward, drop, modify, send to controller. That's the match action model. Internet routing is the higher level problem of how routers learn and compute paths. Inside an AS, you have OSPF or ISIS, link state stuff, and between ASs, BGP, path vector. How do you want to go through this? Big picture first, or
I'm just gonna read through the sections and I want you to summarize it for me, okay?
got it?
Section 1, forwarding, routing, and control. Concept, forwarding. Where should this packet go now? Mechanism, local table lookup and action in the data plane. Routing, what paths or reachability should the network use? Mechanism, distributed protocols or controller applications build state. Concept, destination-based forwarding. Which output matches this destination prefix? Mechanism, longest prefix match. Generalized forwarding. Which actions applies to this packet flow? Match multiple fields, then execute actions. Control plane. How is forwarding state created and maintained? Per router routing logic or logically centralized SDN control.
요약하면 forwarding은 data plane에서
Hey, can
local
you speak
data를
English?
보고-
Can you speak English?
Oh, sure. Forwarding is the data plane doing a local table lookup to decide where this packet goes right now. Routing is the control plane deciding what the paths should be and populating that state. Destination-based forwarding picks the output by longest prefix match. Generalized forwarding matches on multiple header fields and then takes some action. And control can either live in each router or be logically centralized like an SDN. But
Go on.
And the key takeaway is separating fast packet handling from slower decision making.
Okay, what's the difference between forwarding and routing?
Forwarding is local and immediate. Take a packet, look it up in a table, send it out the right interface. Routing is global and strategic. Run protocols to learn the network and fill those tables. One's a quick lookup, the other's the process that builds the lookup.
What's the difference between routing and control plane?
Routing is the function, computing and choosing paths. The control plane is the part of the system that actually runs that logic and installs the resulting state. In distributed routing, each router has its own control plane. In SDN, much of it is pulled out into a controller.
What is SDN short for? Actually, the next section is per router versus SDN control. Let me read that. Traditional per router control. Routing components run in routers and exchange protocol messages. Each router computes local forwarding state. SDN, a logically centralized controller, maintains a network-wide view. Network control applications calculate policy or state. The controller programs data plane devices. Logically centralized does not require one physical machine. Production controllers are commonly replicated or distributed for scale and fault tolerance.
Right. That section saying, in the traditional model, each router runs the protocols and computes its own state. In SDN, software-defined networking, a controller has the big picture view and programs the devices. Logically centralized means one brain in concept, but in practice it's often a distributed or replicated system for scale and resilience.
So a logically centralized controller maintains like a logically coherent path for different routers?
Yeah, it keeps a consistent network-wide view and pushes rules to all routers so they behave coherently, instead of each box figuring it out on its own.
Alright, do not confuse logical and physical centralization. SDN offers a logically unified control abstraction. It does not mean every packet is sent to one controller or that the whole network fails if one server stops. Routine packets remain in the data plane and controller systems can be replicated.
Exactly. Logical centralization means unified decision making, not one physical box. Data packets still flow locally, controllers can be clustered for scale and failover.
Controller meaning.
The controller is the software that holds the network view, runs control apps, and programs the data plane by installing rules. It's a control brain, but it's not in the data path for every packet.
Cool. So let's say a router shares like a logically centralized controller. Does that mean this router does not have a controller?
1 second. Not necessarily. In an SDN setup, the router mostly just has the data plane. The controller lives elsewhere and pushes the decision logic. The router keeps some local agent software to talk to the controller and apply rules, but it's not doing the main routing decision making on its own.
Interesting. Okay. 2. Generalized forwarding. Match plus action abstraction. Generalized forwarding treats a switch or router as a set of flow tables. A packet is parsed into matchable fields. The device finds the highest priority matching rule, updates counters, and executes its instructions or actions. Rules can use fields from multiple headers rather than only the destination IP prefix.
Summary. A switch or router matches packets on multiple header fields, picks the highest priority rule in a flow table, and then runs actions like forward, drop, or modify instead of only using destination IP.
What kind of header fields would it use?
Things like source and destination IP, protocol type, TCP or UDP ports, VLAN tags, basically multiple layers, not just the IP destination.
What does it mean by highest priority matching rule?
When more than one rule could match a packet, the device uses the one with the highest priority value. So there's a deterministic choice.
For instance, what would the matching rules be?
Hang on. Think if then. For example, if destination IP is 10.0.0.5, then forward to port 1. But if destination IP is 10.0.0.5 and TCP destination port is 443, then forward to port 3. If a packet matches both, the higher priority rule wins. Or match source subnet plus protocol and drop. Basically any combination of header fields with an action, and priority breaks ties.
Okay. Flow entry components. Component, match fields. Purpose, identify traffic or metadata. Example, ingress port, Ethernet address or type, VLAN, IP addresses, prefixes, protocol, TCP UDP ports. Priority, resolve overlapping matches. Counters, measure rule use, packets, bytes, or duration. Instructions, control pipeline processing. Apply or write actions, go to another table, update metadata. Actions, change packet treatment, forward to port or group or controller, drop or modify fields, push or pop headers. Timeouts, expire temporary state, idle or hard timeout.
Summary. A flow entry has match fields, a priority to break ties, counters to track usage, instructions to control the pipeline, actions that say what to do, and timeouts that expire the rule.
I get everything, except what's the difference between instructions and actions?
Actions are the actual things done to packets, like forward or drop. Instructions say how to process through the pipeline, like apply these actions or go to table N.
And there are multiple tables in one router?
Yes, in a pipeline design, there can be several flow tables, and instructions can send a packet to the next table.
No. Example policy pipeline 300 TCP destination port 22 from guest VLAN action drop 250 IPv4 destination 10.1.0.0/16 output internal uplink 200 TCP destination port 443 set Q1 output WAN WAN 0 all send to controller or default output.
Summary, that's a sample policy stack. Highest priority blocks SSH from the guest VLAN. Next sends a specific internal IPv4 prefix to the internal uplink. Then HTTPS traffic gets queued and sent out the WAN. And anything else falls through to a default action like send to controller or default forward.
I don't understand the first one. What does it mean by block guest SSH?
It means if traffic comes from the guest VLAN and is trying to use SSH, TCP port 22, drop it. In other words, prevent guest devices from making SSH connections through this switch.
Understood. And this is port 22 is the SSH port, which means what?
Right. It's used for secure shell remote login, basically remote command line access. So blocking it stops guests from SSHing into internal machines.
And what's port 443?
That's HTTPS, secure web traffic. That rule's saying put it in a certain queue for QoS and send it out the WAN.
Send it out the WAN. Wherever it's coming from?
Let me check that. It's traffic that arrives at this switcher router and matches the rule, not where it physically comes from. Output WAN just means forwarded out the interface that connects to the wide area network, i.e. towards the internet.
Okay, so port 22 is into the internal machines and 443 would be out the internet?
One moment. Not quite. The port number itself doesn't mean in or out. It just identifies the application. The rule decides the direction. In your example, port 22 from the guest VLAN is dropped, and port 443 is sent out the WAN because that's what the policy says, not because 443 inherently means internet. You could have internal 443 traffic too with a different rule.
I understand it, but I mean, in this case, port 443 is out the internet and port 22 is into the SSH.
Hang on. For this policy example, yeah, you can think of port 22 as attempted SSH into internal machines being blocked and port 443 as typical web browsing going out to the internet. Just remember, that's this policy's intent, not something inherent about the port numbers.
And what sets these kind of policies?
One moment. The network admin sets them. In a traditional network, each router is configured individually. In SDN, the admin defines high-level policies and the controller compiles them into flow rules and installs them on the switches. Alright, let's see. Tables and pipelines. Open flow style devices may process several tables. An early table can classify ingress traffic, a later table can apply security policy, and another can forward. Metadata can carry classification between tables. The exact supported fields or actions depend on the device and specification version. Summary. Packets can go through multiple flow tables in sequence. Early tables classify, middle tables enforce policy, later tables forward. Metadata passes context along. Exact fields and actions depend on the hardware and spec version.
Give me an example.
Suppose a packet arrives. Table 0 tags it as guest based on VLAN and sets metadata. Table 1 checks guest plus TCP port 22 and drops it. If it isn't port 22, table 2 might send guest web traffic out the WAN. Each table has a narrow job. Together they implement the full policy.
Okay. Reactive versus proactive. Proactive. Controller installs rules before traffic arrives. Low first packet latency and predictable behavior. Reactive. A table miss sends information to the controller, which decides an install state. Flexible, but adds first packet latency and controller load. Hybrid. Broad
Summary.
proactive, defaults plus reactive handling for selected traffic.
Right. Proactive pre-installs rules for speed, reactive installs on demand for flexibility, hybrid mixes both.
Advantages and limitations. Advantages. Unified programmable policy across devices. Fine-grained multi-field treatment separates control applications from forwarding hardware. Network-wide optimization and automation. Rapid deployment of new control logic. Limitations. Controller or application correctness becomes critical. Flow table capacity is finite. Southbound latency and consistency matter. Interoperability and operational debugging can be complex. Data plane features remain hardware dependent.
Summary. You get centralized programmable control and fine-grained policies, but you have to worry about controller correctness, table limits, latency, and hardware differences.
Critical distinction. Generalized forwarding is a data plane behavior. SDN is a broader control architecture that can populate generalized flow tables. OpenFlow is one protocol or specification family for controller switch interaction. It is not synonymous with all SDN.
Summary. Generalized forwarding is the data plane model. SDN is the bigger control architecture that can program it. OpenFlow is just one-way controllers talk to switches, not the definition of SDN.
What's the difference between OpenFlow and SDN? How does OpenFlow implement SDN?
Let me check. SDN is the architecture. OpenFlow is one way to do it. A useful analogy, SDN is like deciding to run a company with a central manager. OpenFlow is like the language that manager uses to tell employees what to do. So SDN defines who makes decisions, a controller, and OpenFlow is a protocol that lets that controller install flow rules on switches. SDN could use other protocols too. OpenFlow is just one.
Wait, OpenFlow is just having a distributed table, right? Distributed tables inside the controller?
One sec. Not exactly. The flow tables live on the switches. The controller computes rules and sends them down. OpenFlow is the way the controller talks to the switches to install those table entries. So the tables stay local to each switch, but the controller manages them centrally. OpenFlow isn't a distributed table inside the controller.
Okay, so the tables live inside the switches. Generalized forwarding means the switches then match the headers of the packets to the table and chooses the most prioritized forwarding output.
Yes, that's right. The switch matches packet headers against its local flow table, picks the highest priority match, and applies the action.
And OpenFlow just means many tables?
Let me check. Not quite. OpenFlow doesn't mean many tables. Multiple tables is a switch design choice. OpenFlow is just the protocol used to program those tables. Think generalized forwarding is what the switch does, flow tables are where rules live, OpenFlow is how a controller programs them, and SDN is the larger architecture.
Wait, what does OpenFlow mean?
It's just the name of a protocol for controller to switch communication.
What does it do?
It lets the controller install, modify, or remove flow rules on the switch. Basically, it's how the controller tells the switch, here's the new rule.
Give me an example of another protocol.
Lendychik. P4 runtime is one. It also lets a controller talk to programmable data planes. Another is netconf yang, which is used more for configuring devices than for pushing flow rules.
So OpenFlow basically has the controller communicate flow rules to the tables inside the switches.
Yeah, the controller sends flow table entries down to the switch. Install this match action rule, will update it, delete it, and so on.
Okay. Number 3, routing algorithm foundations. Graph model. Represent routers or routing entities as nodes and links as edges with costs. A path cost is commonly the sum of edge costs. Costs can be configured from bandwidth, policy delay, or operational objectives. Many deployed IGP metrics do not track instantaneous traffic load because rapid feedback can destabilize routes.
Summary. Model the network as nodes and links with costs. Routing picks paths minimizing total cost. Metrics are usually stable rather than rapidly load-based to avoid route flap.
What's IGP?
Interior Gateway Protocol, meaning routing protocols used inside one autonomous system, like OSPF or ISIS.
Okay. Classification. Information scope. Alternative A. Global. Each node obtains topology or link state database. Alternative B. Local or neighbor. Exchange distance information. Computation. Alternative A. Centralized algorithm in the informational sense. Alternative B. Distributed iterative computation. Dynamics. Alternative A. Static or infrequent. Alternative B. Dynamic after topology or policy changes. Reaction. Alternative A. Periodic. Alternative B. Event triggered, often with periodic maintenance.
Summary of the classifications. Some protocols give each router a full global view and a centralized computation style like link state. Others use only neighbor information with iterative distributed computation like distance vector. Updates can be periodic or event triggered, and dynamics range from mostly static to reacting to topology or policy changes.
And this means inside every router?
One sec. Yes, it's referring to what each router knows and computes. In a link state approach, each router has the full topology. In a distance vector approach, each router only knows what its neighbors tell it and iteratively refines routes.
And that would not be centralized. What's it called again? Centralized SDN, right? The local neighbor alternative.
Hang on. Exactly. The local neighbor approach isn't SDN. Both link state and distance vector are traditional distributed control planes. SDN's controller computes and pushes rules centrally. Hybrid now.
Okay. So link state algorithm. Discover neighbors and link costs. Flood link state advertisements so routers obtain a consistent topology database within the domain or area. Each router runs Dijkstra's shortest path first algorithm from itself. Install next hops for least cost destinations, possibly using equal cost multipath. Changes trigger new advertisements and recomputation subject to timers or controls.
Summary. Routers discover neighbors, flood link state info, build the same topology database. Each runs Dijkstra to compute least cost next hops and recomputes on changes, often with dampening.
And this is global?
Yes, in link state, each router ends up with the same global topology view for that area or domain, even though the computation runs on every router. So global knowledge, but distributed execution.
Okay. Dijkstra idea. Maintain a settled set and whose least costs are known. Repeatedly choose the unsettled node with smallest tentative distance, add it to n prime, and relax its outgoing edges. D of v is min of d of v and d of w plus the cost of w to v. With suitable data structures, the algorithm scales much better than a native table scan. Okay, got it. Got the Dijkstra. Distance vector
Right.
algorithm. Each node x maintains a cost estimate of cost y to each destination y using neighbor v with link cost x to v. The Bellman-Ford relationship is dxv is equal to min v of cost x plus xv plus d of y. Nodes exchange vectors with neighbors and update asynchronously until stable.
Summary. Each router keeps best known distances, exchanges them with neighbors, and updates until everyone converges.
Okay. DV failure behavior. A cost decrease can propagate quickly because neighbors learn a better path. A failure cost increase can produce routing loops and count to infinity. Neighbors mistakenly advertise routes through one another. Split horizon poisoned reverse prevents certain two-node loops by advertising infinity back toward the next chosen hop. Poison reverse does not eliminate all loops involving 3 or more nodes. Operational protocols use additional timers, sequence or version information, feasibility rules, or topology approaches, depending on the design.
Summary. Distance vector reacts fast to improvements, but can loop or count to infinity on failures. Mitigations help, but don't solve every multi-node loop.
Alright, LS versus DV. Let's see more. Okay, dimension, knowledge, link state, topology database, distance vector. Wait, whoa. I thought distance vector was just one, like, implementation of link state.
One sec. They're actually distinct families. Link state floods the full topology to everyone. Each router runs Dijkstra. Distance vector only exchanges distances with neighbors and iterates, not an implementation detail.
But they're both global, right?
Not quite. Link state gives each router a global topology. Distance vector doesn't. It only knows neighbor summaries, which eventually approximate global shortest paths once converged.
So it is global. Because they should converge eventually.
Careful. It converges to correct routes, but each node still lacks a global map. It just has next hop distances. So outcome may be globally optimal, but knowledge remains local.
But link state, the knowledge is global.
Yes, in link state, everyone has that same topology database. That's why they all can run Dijkstra locally, yet consistently. DV never builds that full map. It just iterates neighbor distances.
Alright. So what does the distance vector do? It just knows its neighbor cost, and then it just sends it to the least cost from its knowledge.
Yeah, pretty much. Each node keeps a table of best known distances, updates from neighbors, applies Bellman-Ford, and picks the current best next hop.
Okay. I guess that makes sense. Autonomous systems and routing hierarchy. Why hierarchy? The internet cannot run one global shortest path protocol under one administrator. It is divided into autonomous systems, each operated under a common administrative policy and identified by an AS number. An AS uses an interior gateway protocol for internal reachability and BGP for reachability or policy among ASs.
Summary. The internet's too big for one global protocol. It's divided into autonomous systems, each with its own internal routing, and BGP handles routing between them.
What's BGP?
BGP is the Border Gateway Protocol. It exchanges reachability between autonomous systems and enforces policy.
Okay. Scope, intradomain, or IGP. Reach destinations inside one AS and reach chosen exits. Examples, OSPF or ISIS, configured link metrics. Interdomain, or EGP. Exchange prefix reachability and enforce business or traffic policy among ASs. Examples, BGP or path attributes and policy. Scope, forwarding. Use selected next hop state to move each packet. Longest prefix match plus recursive next hop resolution.
Summary. Inside an AS, OSPF or ISIS handles internal routing. Between ASs, BGP exchanges prefixes and enforces policy, and forwarding uses longest prefix match plus next hop resolution to move packets.
So now you gotta tell me where link state would be used, in what scope, and where generalized forwarding would be used, in what scope.
Link state is an intra-domain IGP thing, inside one AS. Generalized forwarding is data plane behavior. It applies wherever your device is supported, within an AS or at the edges, not limited by routing scope.
So what about BGP? What would they use?
BGP is the intra-domain protocol for between ASs.
Alright. Policy relationships. Customer pays provider for transit or reachability. Peers exchange traffic for their customers under an agreement, often without providing unrestricted transit. A stub AS primarily carries its own traffic. A transit AS carries traffic between other networks. Import policy decides which received routes are accepted or preferred. Export policy decides which routes are advertised. The commercially preferred route can outrank the shortest AS path.
Summary. BGP routing is driven by business policy. Customers, providers, peers, import, export filters. Commercial preference can beat shortest AS path.
Okay. OSPF, intra-AS link state routing. Core operation. OSPF is a link state interior gateway protocol. Routers discover neighbors using hello packets, form adjacencies, originate link state advertisements, and reliably flood LSAs. Routers in the same area build synchronized link state databases and run shortest path first computation to create routes.
Summary. OSPF uses hellos to find neighbors, floods LSAs so every router in an area has the same database, then runs SPF to compute routes.
Step by step. Hello protocol discovers or maintains neighbors and participates in designated router election on multi-access networks. Adjacent routers synchronize link state databases. Routers originate LSAs describing relevant links, networks, matrix, and reachability. Flooding distributes newer LSAs throughout the appropriate scope. Each router runs Dijkstra from itself and derives next hops. Topology changes generate new LSA and trigger controlled recomputation.
Summary. Hellos form adjacencies and elect DRs. Routers sync LSDBs, flood LSAs, run Dijkstra, then recompute on change.
What does flooding mean?
Flooding means reliably spreading LSAs to all routers in the area so everyone has the same database.
What did link state mean again?
It means each router learns the full network topology for its area via LSAs and computes shortest paths locally.
What was LSA?
Link state advertisement, the message OSPF routers flood to describe links and prefixes.
Like costs, right? Like it's kind of like the map of nodes and edges, right?
Yeah, exactly. Nodes, links, costs, all that topology data. Enough so every router builds the same map and then runs SPF.
Alright. Areas. Area 0 is the backbone in normal multi-area OSPF design. Area border routers connect areas and summarize or advertise reachability according to OSPF rules and configuration. Internal routers need detailed topology for their own area, but not necessarily every link in all areas. Hierarchy reduces flooding or SPF scope and database size while adding design complexity.
Summary. Area 0 is the backbone. ABRs connect and may summarize routes. Routers keep full detail for their area, not all areas, reducing overhead but adding design complexity.
So this is kind of like a hybrid between global and localized.
Yeah, that's a good way to put it. Full topology within an area, summarized between areas, hierarchy for scaling.
Alright. OSPF facts. Property. Protocol type. Interview note. Link state IGP within an AS. Transport. OSPF v2 runs directly over IP protocol number 89, not TCP or UDP. Matrix. Configured cost. OSPF does not mandate one universal physical formula. Equal cost path. Supports equal cost multipath. OSPF v2 or OSPF v3. OSPF v2 is used for IPv4. OSPF v3 was designed for IPv6 and has evolved extensions. Security. Authentication mechanisms depend on version and concurrent extensions. Avoid treating legacy MD5 as modern universal behavior.
Summary. OSPF is a link state IGP over IP protocol 89. It uses configured costs, supports ECMP v2 for IPv4, v3 for IPv6, and security mechanisms vary by version. Don't assume MD5 is still state of the art.
Okay. Okay. Moving on. BGP, inter as path vector routing. Inter AS path vector routing. I was actually curious about this. Purpose, BGP exchanges network layer reachability information between ASs and distributes it within an AS. A route associates a destination prefix with path attributes. BGP is path vector and policy based. It carries an AS path and other attributes, allows policy filtering or preference, and does not simply compute the globally shortest physical path. You there?
I'm here.
Did you hear what I said about BGP? BGP exchanges network layer reachability information between ASs and distributed within an AS. A route associates a destination prefix with path attributes. BGP is path vector and policy based. It carries an AS path and other attributes, allows policy filtering or preference, and does not simply compute the globally shortest physical path.
Summary. BGP carries prefixes plus path attributes, runs between ASs, inside an AS via IBGP, and policy drives path choice, not pure shortest path.
All right. Blah, 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 blah. So BGP runs vector based, path vector. So BGP runs DV.
Sort of, one sec. Path vector is related to distance vector, but BGP carries the full AS path and policy attributes, not just a distance metric. That lets it avoid simple DV issues and enforce policy. So similar family, but not the same as classic DV.
What is an AS path?
It's the ordered list of AS numbers a route has traversed.
Okay, I'm gonna read through the advertisement example. AS65030 originates prefix 203.0.113.0/24 and advertises it to AS65020 using eBGP. AS65020 applies import policy. If accepted, it distributes the route internally using iBGP. When advertising onward to AS65010, AS65020 prepends itself, yielding AS path 65020, 65030. AS65010 rejects an advertisement containing its own AS number, preventing an AS level loop. Each AS selects its preferred route and exports only routes permitted by policy.
Summary. One AS originates and advertises. The next applies import policy, propagates via iBGP, prepends its ASN on export, loops are avoided by detecting your own ASN, and each AS picks and exports routes per policy.
How does the ASs know like where to go by looking at the prefix?
It matches the destination IP to the longest prefix in its routing table, which BGP has filled.
So we're going to AS65020 for prefix 203.0.113.0/24 because it's in the table, routing table.
Let me check that. Exactly. If the router has a route for that prefix in its table, installed from BGP after policy checks, it forwards toward the next hop AS listed there.
And how is the next hop for ASs computed again?
One sec. Good question. 2 steps. First, BGP picks the best AS level route using AS path and policy. Then, inside your AS, the IGP like OSPF gets the packet to the chosen border router. So BGP chooses the exit AS and the IGP gets you there.
Wait, what does the IGP do?
It handles internal routing within your AS. It gets the packet to the chosen border router.
And border router meaning what?
The router at the edge of your AS that connects to another AS.
Okay. Wait, how does the BGP know where to go? Like which AS to go to?
Let me check. BGP learns from others. AS65030 says, I can reach this prefix. AS65020 passes that along. And AS65010 chooses among what it hears, like asking for directions, then picking a route.
I mean, why does 65030 advertise this prefix to 65020?
One moment. Because 65030 owns that prefix. It's basically saying, if you've got packets for this destination, send them to me. Everyone passes that along so the internet knows how to reach it.
Oh, okay. Okay, got it. So this is pre-computing a path for a certain prefix.
Think of it like, I can reach this prefix, and here's the AS path. Each AS picks its best route ahead of time, so when packets arrive, forwarding is quick.
Damn, I thought this was while forwarding. So advertising a prefix means I can get you to this prefix. Like this prefix is within my AS.
Exactly. I'm the origin for that block, or I know a path to it. And others use that to send traffic in the right direction.
Oh my god, got it. That makes a lot of sense. Okay, going on. Simplified best path reasoning. Operational BGP selection is implementation and policy specific, but a safe conceptual order is consider only accepted valid routes, prefer policies such as highest local pref, often prefer shorter AS path, apply other attributes such as origin or med under defined conditions, prefer eBGP over iBGP in common selection, then use the lowest IGP cost to the next hop, and deterministic tiebreakers. Do not memorize this as one universal vendor list.
Summary. BGP best path is policy driven. Only consider valid routes, local pref usually first, then AS path length, then other attributes, tiebreakers later.
What does it mean by prefer eBGP over iBGP in common selection?
One moment. It just means all else equal, if a router learns two routes and one is learned directly from another AS, eBGP, and the other is learned indirectly via another router inside its own AS, iBGP, it picks the eBGP route. It's basically prefer the directly learned external route. But remember, that's just one tiebreaker later in the decision process. Local pref and AS path length come earlier.
So let's say a path is learned by an iBGP. What would happen? Would it prepend the iBGP router that taught this path?
One sec. Good question. No, iBGP doesn't prepend. The AS path stays the same inside the AS. Only eBGP adds your AS number when advertising to another AS. Inside, iBGP just carries the same AS path, no extra AS number gets inserted. That way the AS path reflects AS hops, not internal routers.
Alright, hot potato routing. After higher priority policy choices are equal, an AS may choose the exit with the lowest internal IGP cost to the next BGP next hop. This gets traffic out of the AS quickly. It minimizes the local AS's internal cost, not necessarily end-to-end latency or global path cost.
Summary. Hot potato means hand traffic off as soon as possible to the nearest exit. Lowest internal cost, not necessarily best end-to-end performance.
Okay. Import-export policy. Prefer customer route. Example, revenue or customer service often outranks peer or provider routes. Do not provide peer-to-peer transit. Do not export one peer's routes to another peer. Provider export. Advertise customer prefixes broadly. Advertise selected upstream or peer routes to customers. Traffic engineering. Adjust local pref communities, AS path prepending, med, or more specific advertisements carefully. Safety. Filter invalid or unexpected prefixes and paths. Default reject export without explicit policy is a modern safeguard.
Summary. Prefer customer routes, don't leak peer routes, advertise customer prefixes widely, use attributes carefully for TE, and default deny exports.
I kind of don't get the customer part of this. What does the customer mean?
One sec. Here, customer means a network that pays your AS for transit. You carry their traffic to the rest of the internet. Peers are like equals, exchanging traffic. And providers are upstream networks you pay.
So I would be a customer?
Not as an individual user. In this context, customer is an entire network or ISP that pays another network for connectivity. So your home ISP is a customer of a large...
Oh no. Go on. So what is the customer whatever relationship?
Right. So in BGP terms, customer is it's an AS that pays another AS for transit. So your home ISP, for example, is a customer of a bigger provider. That provider carries the customer's traffic to the rest of the internet. And then peers are more like equals. They exchange traffic for their own customers, but they don't provide open-ended transit to everyone. So providers are upstream networks you pay, and these relationships drive import and export policy decisions. For example, you usually prefer and export customer routes widely, but you'd restrict peer routes to avoid providing unwanted transit.
Okay. BGP convergence and safety. BGP is incremental and asynchronous. Convergence can take time after failures or policy changes. Route withdrawals and alternate advertisements propagate according to policy and timers. Misconfiguration or route leaks or hijacks can propagate incorrect reachability. Origin validation and filtering improve safety but do not turn BGP into an authenticated shortest path protocol. Aggregation reduces table size. More specific routes can intentionally or accidentally override aggregates.
So, yeah, convergence is eventual, not instant. And during that time, bad info can spread. So, operators use filtering, route validation, and careful policy, but it's still not provably shortest path safe. And aggregation shrinks tables, but more specific routes can override those aggregates.
Okay. 7. How internet routing fits together. An originating network obtains an address prefix and AS connectivity, then originates or advertises the prefix through BGP. Neighboring ASs apply import policy, select routes, distribute them via IBGP, and export permitted routes to other ASs. Within each AS, an IGP, such as OSPF, provides internal routes to routers and BGP next hops. A router resolves the selected BGP route to a reachable next hop and installs forwarding entries. Packets use longest prefix matching in the data plane and traverse the chosen AS path hop by hop. Failures or policy changes trigger IGP and or BGP updates. After convergence, forwarding state reflects the new selection. Okay, be really thorough and go slowly with this one because I feel like this is the most important section.
Sure. Let me take it slowly. This really is the capstone because it ties BGP, OSPF, forwarding tables, and longest prefix match together. So imagine your AS 6520 that owns prefix 2030/24. It advertises that prefix outward via BGP. Neighboring ASs receive it, apply their import policies, maybe accept it, then they pass it internally using IBGP so their border routers know. When that AS advertises onward, it prepends its own AS number to the AS path, telling others, reach it through me. Other ASs repeat this, so no packets are flowing yet, it's all route knowledge. Each AS selects a best route, but doesn't just pick the shortest path blindly. It applies policy preferences like customer routes first, then AS path length, then other attributes. Once chosen, the IGP, like OSPF, figures out how to reach the selected border router inside your AS. So BGP picks the exit, OSPF gets you to that exit. After that, the router installs forwarding entries, and when a packet arrives, it simply does longest prefix match in that table. So the packet hops through the chosen AS path, router by router, not rerunning BGP each time. If a failure happens, like a link breaks between two ASs, BGP sends withdrawals, and OSPF may recompute internal paths. Once convergence finishes, forwarding tables update, and new packets follow the new path.
Okay. When a packet travels an AS path, it should also travel a router by router, hop by hop within an AS, right? Until it gets to the exit router.
Exactly. BGP decides which exit router to use, and then inside the AS, the IGP computes the path, hop by hop, to that router. Once the packet reaches the exit router, BGP's job for that decision is essentially done. From there, the packet moves using the forwarding table entries that OSPF helped compute. So within that AS, it's strictly hop by hop forwarding, not BGP reevaluation.
In this example, we're not using generalized forwarding, right? We're using longest prefix matching.
Right. This description is the classic model, IGP like OSPF for internal routing and BGP for interdomain routing. Generalized forwarding would be a more SDN style approach. But here, we're just talking classic longest prefix match forwarding, after OSPF and BGP have already done their routing decisions.
Okay. Okay, let's talk about SDN control plane. Architecture, data plane devices. Role, execute flow table match or action at line rate. Southbound interface, communicate state events and commands between devices and controller. Controller platform or network OS maintains topology or device state and exposes abstractions or APIs. Network control applications. Routing, access control, load balancing, traffic engineering, monitoring. Northbound API lets applications express desired behavior and query network abstractions. Controller interaction. Device reports ports, topology events, counters, or table misses. Controller builds a network view and applications compute desired policy or path. Controller installs, modifies, or deletes flow entries. Devices forward matching packets locally and report selected events. Consistency, failover, rule ordering, and safe updates are essential engineering concerns.
One sec. Right, that's the SDN take compared to traditional routing. Data plane devices, the switches, they just execute match action tables at line rate. The southbound interface, earlier likened to OpenFlow, talks between controller and switches. The controller platform, or network OS, keeps a global view of the topology and state instead of every router running OSPF or BGP separately. Then network control applications like routing, access control, load balancing, traffic engineering, they all ask the controller for what policies they want. And the northbound API connects those apps to the controller. So in practice, a device reports ports, counters, or table misses up to the controller updates its global view, the applications decide the policy, and the controller computes flow rules and installs them into the switches via the southbound interface. After that, the switches forward packets locally, line rate, and only send events back when something changes. The tricky part, like you said, is consistency, failover safety, and rule ordering. When rules update across multiple switches, you have to avoid transient black holes or loops. So even though the forwarding itself stays local, the control logic acts centrally, which is the trade-off that makes SDN powerful but engineering intensive.
Okay. Question. SDN control plane is within an AS, right? It has nothing to do with the eBGF.
Let me check. Yeah, generally right. The SDN controller typically controls one AS or one administrative domain. So inside your AS, the SDN controller has the job of deciding how traffic moves. When traffic needs to leave your AS and go to another, that's where eBGP comes into play. So SDN and BGP aren't mutually exclusive. You can use BGP at the borders and still use an SDN controller to manage forwarding inside the AS. For exams, it's safest to say BGP chooses between ASs while OSPF or an SDN controller decides how traffic moves inside your AS.
OSPF and SDN, aren't they both centralized? Not centralized, but global, at least.
One sec. Kind of, but not the same kind of global. OSPF has global knowledge, but not centralized control. Every router runs Dijkstra itself. SDN has global knowledge as well, but it is centrally controlled by the controller, which computes and pushes the rules. So global but distributed in OSPF, global and centralized in SDN. That's the distinction your instructor's likely probing.
How does SDN compute root?
Hang on. Good question. There's no single fixed algorithm. The SDN controller has a global view, so it can run whatever the network application asks for. Shortest path like Dijkstra, load balancing across links, traffic engineering to avoid congestion, or security policies that steer traffic through firewalls. It computes the needed paths or rules based on that objective, then installs the resulting flow table entries into the switches using a southbound protocol like OpenFlow. So, unlike OSPF, where every router always runs Dijkstra, SDN doesn't prescribe one algorithm. The controller runs whatever algorithm the desired policy requires.
So IGP, let's say I'm running an OSPF path within an AS, and I have a destination prefix that goes to another AS, which is reachable on an export router within our AS. What would be the next hop on a single router? And what would be the next hop on a single router, and how would it be calculated for the packet with this specific destination IP?
Let me think. Good question. Let's step through one packet. Say you're in AS65010 and the destination IP matches 203.0.113.024, and BGP already learned that it's reachable via a border router. So the BGP part tells which border router is the exit. Then OSPF figures out how to reach that exit router hop by hop. So the next hop in your router's table is just the first router on the shortest IGP path toward that border router, not the final destination IP. Each router repeats that same logic until the packet reaches the border router, which then sends it out toward the neighboring AS. So BGP picks the exit, and OSPF picks the next hop to get to that exit.
그렇군. Got it. Wow. Yowzas. Gah. 왜 이렇게 길어? Oh my god. I don't even want to know. I don't even want to know. Oh ho! 죄송. 아. 아. Okay. Can't I just do... Can I just do dpij? Number of increasing subsequences of length I, ending at j. Ending with nums j. I mean, it has to be longest increasing. Uh-huh. It only has to store one number. Whoa. What is going on? Plus equals n? No. Oh, 뭐해? 아니, 그게 아니라 n 이게 뭐야? 아, 아, 그치. 자, 6개는 2개다. 5개라고? That should be 0. Honestly, it should be 0. It should be 1. 이거는 1 1 1 1 5개가 또 있어, 그러면? 아, 이런. 아, 근데 이거 플러스 이꼬 넘이 왜 아니지? 아, 잠깐. 잠깐만. 하지 마라. 아니네. 서희. 오, 그래? 오호, 오호. 나이스, 나이스. 나이스. 자, 다음 거 보자. am I doing? 여기구나. What? 네. Why? 어, 3. 3. 알아? 음. 뭐야? 8, 2, 0. 뭐야? 뭔데? 에? 아, 뭐하냐? 아, 진짜. 뭐하냐, 진짜. 아니야, 진짜로 뭐하냐. 나이스! 너무 잘해. 너무 잘해. (1048)
아니지.
왜?
가양동. 예, 잠시만.
아 이거 왜 떼? 이거 왜 떼줘?
머리카락.
이거 왜 떼줘? 기분 나쁘게. 안녕하세요. 안녕하세요. 반갑습니다. 또 여기서 뵙네요, 여러분. 오늘은 날이 밝아가지고 되게 화사하네요. 그죠? 자, 오늘 이제 굿즈 포장을 지금 하고 있고요. 포장하다가 중간에 햄버거 먹고 있었는데 방송 키고 먹을 걸 라고 생각이 들어가지고 먹다가 켰어요. 지금 저 혼자 있는 건 아니고 하마랑 뽀님이랑 행님이랑 교님이랑 저의 오늘의 임무는 햄버거 먹고 말씀드릴게요.
재고가 생각보다 많아서 굿즈 홍보하려고
맞아요. 여러분 주문 좀 해주세요. 저의 오늘의 임무가 있어요. 여기 엽서에다가 사인을 해서 이제 같이 넣어드리려고 하거든요. 쓰는데 밑에 한마디 쓰는 거가 사실 이제 멘트가 다 떨어졌어요. 멘트 추천 좀 해주세요. 제가 열심히 머리를 맞대고 생각해가지고 정말 감동적인 글귀들을 적어놨는데 다 떨어져가지고 근데 이거 좀 닦고 올게요. 자, 씻었고요. 제가 티셔츠 모델을 소개시켜드리겠습니다, 여러분. 모델, 이거 방망이 왜 들고 오세요?
안녕하세요. 안녕하세요.
자, 티셔츠 모델
안녕하세요.
하마님이랑 뽀님 어때요, 여러분? 예쁘죠? 하마가 입으면은 이 판매를 하려면 좀 문제가 생길 것 같아요.
아니. 저 100kg인데 저도 입을 수 있어요.
이거 괜찮을까?
여기가 일반적인 젊은 사람.
형님, 연극 잘 어울리네. 앞으로 중요한 일 있어요. 이거 입고 갈 거예요?
네? 근데 글씨가 진짜 생각한 것보다
네?
막 사람들이 신경 쓸 만한 글씨
그죠. 별로 그렇게 막 안 보여요, 잘.
참고로 제가 김선우 티셔츠 맨 처음 것도 아직까지 입어요. 10년이 지났는데도.
그거랑 똑같은 재질이어가지고 이것도 오래 입을 수 있을 거예요.
이것도 오래 입을 수
네.
사용용도 한번 보여드릴게요.
사용용도 한번 보여드리겠습니다.
하나 둘
거의
아니 그래도 내 얼굴인데
여러분 이거 많이 사주세요. 지금 티셔츠가 팔려야 돼요. 저희 라이브 커머스거든요. 지금부터 주문이 많이 들어오면 행복해요.
그래서 제가 사인을 해서 넣어드리고 있습니다, 여러분.
네.
뽀님이 입은 거
이 사이즈요.
이 사이즈.
둘이 지금 사이즈
이것도 이 사이즈.
똑같은 거 입은 거예요, 여러분.
사람 차이에요. 사람 차이.
둘이 옷
죄송한데
똑같은
사람
거예요.
차이예요.
예, 똑같은
사람
거
차이.
입은 거예요, 똑같은 거.
내가 사장 갖고 어디 잡혀 있는 사람 같아.
사실 맞아요, 여러분. 제가 여기서 나가려면은
네.
제가 하마는 100kg.
네네네. 뽀님 바지 좀.
아, 바지는 알려드리면 안 돼요. 바지 정보를 왜 물어봅니까? 바지는 저희 거 아니에요.
내 바지는
네.
내 바지는 관심이
바지,
없나?
바지 정보를 왜 알려달라 그러는
내 바지는
거야?
관심이 없나?
아니. 멘트는 완전 랜덤이에요. 정말 감동적인 것도 있고, 정말 슬픈 것도 있고, 정말.
사인 사면 티셔츠 다 주니. 아니 사인 사면 죄송해요.
사인 사면은 티셔츠 같이 드립니다. 자, 우주 최강 미남입니다. 이거 받으면 되게 기분 좋겠죠? 이모 종룡 그려달라고요? 아, 이모 종룡 제가 그려드릴게요.
일단은 제가 티셔츠 좋은 거 말씀드릴게요. 목이 쫀쫀해요. 목이 진짜 쫀쫀해요. 거짓말 조금 보태서 누가 나 쪼르고 있는 것 같아요. 티셔츠는 뭐다? 목이 쫀쫀해야 돼요. 이래야지 잘 안 늘어나. 빨리 이거 건조기 건조기 여러 번 돌려도 될 정도예요. 요거 괜찮아요. 그리고 어깨선이 약간 오버핏이야. 어깨선이 오버핏이에요. 그래서 마르신 분들은 편하게 입어도 되고, 그리고 저처럼 빵이 두꺼운 사람도 입을 수 있어요.
머리가 커도
머리가
들어가네요.
커도 들어가는 얘가 입고 있잖아요.
제가 지금 입고 있잖아요.
얘가 입고 있잖아요.
네,
얘가.
네. 아, 그리고 뭐 여러 가지 키캡이랑 보여드리겠습니다.
이 차는 이제 제 겁니다.
지금 방송 키고 나서 티셔츠 2개밖에 안 나왔어. 티셔츠 좀 사주세요. 2개밖에 안 나왔대 지금.
또 안 나가면은 어쩔 수 없는 거죠. 방송 중에 티셔츠 몇 장 팔리는지 그렇게 나가려고.
나 약간 상처받을 것 같아.
와, 진짜 배팅 각을 정말 잘 보시네. 아, 근데 뽀님이 좀 초심을 잃은 게 오늘은 샵을 안 갔다 왔대요. 원래 항상 방송 나올 때 샵을 갔다 와야 되는데.
개 빠져.
아, 오늘 저기 샵도 안 갔다 오고 초심 잃었어. 아우 잘.
뭐 마셔?
저 연유라떼 디카페인에 오트밀크 변경해 주시고요. 라이트 바닐라 시럽 추가에 저당 스테비아로 변경할게요.
그리고 아이스 아메리카노 한 잔이야?
아, 내가 내야 되는데.
아니야, 요즘 돈 부족하잖아.
아, 내가 얼른 알바 자리라도 구해가지고 혜빈이 맛있는 거 사줘야 되는데. 나 집 앞에 PC방에서 알바 구하는데 한번 해볼까?
PC방? 괜찮은데?
그치? 카운터만 보면 되고 취준도 같이 준비할 수도 있고.
괜찮네, 한번 해봐. 너무 취준만 해도 좀 에너지 떨어지는 게 있긴 하더라.
그리고 요즘에 데이트할 때도 너무 얻어만 먹는 것 같아서.
괜찮아.
내가 꼭 취준 성공해서 혜빈이 호강시켜줄 거야. 저는 비타민 A 같은 초롱한 눈과 비타민 B 같은 튼튼한 두 다리와 비타민 C 같은 밝은 마인드를 가지고 있는 종합 비타민 같은 사람입니다.
종합 비타민 같은 소리 하고 있어. 오늘 PC방 알바 출근 9시라 했나?
나 그거 그냥 안 하기로 했어.
왜?
PC방이 카운터만 보면 되는 줄 알았는데 생각보다 짜잘하게 할 게 많더라고. 빨리 취직해가지고 우리 혜빈이 여행 보내줘야 되는데.
됐어. 그런 소리 하지 말고 열심히나 해. 뭐야?
택배 왔나 보다.
뭐 샀어?
옷.
너무 많잖아. 왜 옷을 또 사?
필요하니까 사지. 이거 어때? 예쁘지?
뭐 마셔?
첫 콘서트부터 레전드 찍은 코르키스. 이례적인 1시간 40분 공연으로 심각한 눈뽕 조명에 팬들은 눈 뜰 수가 없었고, 따브로 흠뻑 젖은 옷을 갈아입지 않고 단벌 콘서트라는 정점을 찍어버린. 안전요원은 옷까지 맞춰 입으며 핸드폰 내려놓으라 하고 다른 노래 부를 줄 알고 기대했는데 또 영크만 5번째 부르는 중.
조심히 돌아가세요. 비 많이 올 거예요.
비도 안 오는데 성의 없는 소감까지. 결국 14만원 콘서트가 14,000원 호프보다 빨리 끝났다고 함.
그래 그리 쉽지는 않겠지.
쓰라. 에휴 이마.